Hello and welcome to another episode of That 60s Recording Podcast, the podcast that has conversations inspired by the golden era of recording. I am your host, Joe Montague. I hope you've all had a lovely week. Today, this morning, we have the very last lecture from the Ted Fletcher lecture series. I've become very good at saying that. I've been practicing it quite a lot. This lecture is kind of a roundup of everything that we've talked about so far. In fact, as I was reading it, there's quite a lot of sort of copy that he's repeated from previous lectures. Obviously, these were actual lectures that he gave in universities. So some of it's repeated, but I decided that was kind of good in a way. It's a nice way of rounding everything up. It's also worth bearing in mind that at the end, I do interject. There's a little demonstration that he does, which obviously I don't have. But you can listen to examples all over of the things that he's talking about. So when he talks about EQ and compression later on in the lecture, you can go and find examples of this, or just play around in your DAW yourself and get used to the sounds that he's talking about. But I imagine that most people listening to this will have some knowledge of all of this stuff anyway. So yes, the sort of the main point of it is that we're getting, you know, as I keep repeatedly saying, an insight into the mind of Ted Fletcher and how his mind works. So with that in mind, I will do the usual caveat that Ted asked me to do. So his lectures were delivered to universities. In fact, this one was delivered on a series of degree courses. This was a foundation degree course. So some of the terminology he uses and the way he delivers it is probably a little more basic actually than the other ones, which again may be a good thing as a way of rounding it up. But just bear in mind that this was delivered in 2005, so over 15 years ago, sort of 17, 18 years ago, and a lot of things have moved on since then. Not many, the physics hasn't, and the principles behind it haven't, but it's just something to bear in mind while he's talking. So we'll just get straight on. This is lecture number 8, Recording in the Real World. Recording in the Real World. Introduction. Teaching about sound and sound recording inevitably concentrates on the physical properties of sound and how to capture it. I am becoming more and more convinced that this is entirely the wrong approach. It's fine and necessary to learn about the technology of capturing sound and being able to reproduce it again at a later date, but to get anything like a true understanding of what we are really getting into, one needs to understand more about how we hear sound, both physically by studying the ears and the mechanisms within them, but even more importantly, how sound affects us and how we understand what sounds are. Once we have some sort of grasp of what and how we hear, we can start to apply that knowledge to the various parts of the recording process, starting in the studio at the microphone, then moving on to the microphone preamplifier and other necessary or unnecessary parts of the recording chain, up to the recording medium itself, and the ways of monitoring what's going on and how to use it once we've got it. Sound, the stuff of recording. We are taught, parrot fashion, that sound doesn't behave in a linear way like string or water, it is logarithmic. Usually we are told some gee-whiz facts to try to understand scale, but sadly our brains don't work that way and it's a tough concept to grasp. I think the only way to come to terms with sound levels is to think in terms of decibels and try to remember that a 1000-watt amplifier is not that much louder than a 10-watt amplifier. I'm being intentionally flippant about this. At the two ends of the spectrum, to make a sound louder, a lot of extra energy is needed. If a sound is already very quiet, you can take most of its energy away and it won't seem to get much quieter. And what about frequency? We can hear a range of frequencies from about 25 Hz up to around 14 kHz. This can be measured as the frequency response of our ears, but natural and musical sounds extend from as low as 8 Hz up to 40 to 50 kHz. Is this relevant? To answer that question, we need to turn the problem on its head and start to talk about ears. Hearing and perception. From the mid-1930s up to the late 60s, a massive work was done in audio labs studying the biology and the physical limits of human ears. I won't be arrogant enough to dismiss the whole of the research out of hand, but insist that all the work needs to be placed in a context of the knowledge that what we think we hear is very much more important than what some figure on a graph tells us we should be hearing. The mechanism of the ear is reasonably well understood and taught. The path of pressure waves from the outside air causes movement of the eardrum. The bone structures act as impedance converters and transfer the vibrations across the middle ear to the inner ear, where the pressure waves act on sensory cells in the cochlea. The level of understanding of hearing is about on par with the knowledge that a dog usually has 4 legs. To scratch the surface just a little. Extreme frequencies. Physical hearing tests show that we can discern frequencies as notes down to about 30 Hz. Yet in our daily lives, we are subjected to and are well aware of lower frequencies, so-called infrasound. These come from mechanical things such as heating and aircon systems, trains and motors, as well as naturally, storms and wind. At the other end of the spectrum, we are not only aware of frequencies above 15 kHz, but all musical sound contains harmonic information at high frequencies contributing to musical quality. Noise and range. Any discussion about the range of volumes that are heard by the human ear is bound to be complicated. Simplistically, we can hear sounds as low as a pin dropping onto carpet at a distance of 20 feet. Okay, well, I'm just guessing there. Up to a level where pressure of sound causes physical pain. In front of the rig at an AC/DC concert. But within those extremes, hearing does some amazing things. A trip out into the country on a quiet night can easily show how our hearing, note, I'm using the term hearing rather than ears, changes and becomes very much more sensitive than normal. Equally, in a noisy environment, our hearing desensitizes as if it is compensating to make things more comfortable, and that's exactly what it's doing. Where these effects actually take place is debatable. Some of the compression effects take place in the middle ear and inner ear, but I suspect that most of it's in the brain. Quality. So far, we have considered sound and hearing in terms of ranges of perception. It's like describing a painting as various coloured patches on a flat plane. But eventually, we want to move towards an understanding of recorded or created performance, and so we need to know more about what our hearing considers good and acceptable, and if there are any aspects of not so good that have to be watched out for. Distortion, just a look. The simplest musical note is a sine wave. This is the sound of a single frequency, devoid of harmonics. If a sine wave is distorted by compressing or constricting just the top or bottom of the wave, then harmonics appear in the sound. These harmonics are called even order harmonics, and they are musically related to the fundamental frequency. The second harmonic is 1 octave above the fundamental, the fourth is 2 octaves, and so on. But if the sine wave is distorted symmetrically, top and bottom, the resulting harmonics are called odd order, 3rd, 5th and 7th harmonics, and these frequencies are musically unrelated to the fundamental frequency. They sound harsh and unnatural. I have my theories as to why even order distortion sounds acceptable and while odd order doesn't. A part of the answer probably lies in the way the cells respond in the inner ear. They are tiny hairs of different lengths that sway and trigger impulses from their roots. Another possibility is that it is because almost all harmonics that occur in nature are even order. The whistling of the wind, a human voice, the song of birds, are all rich in second order harmonics. Microphones and microphone preamps. A lot of this is quite simple stuff, but I say it just in case. The main types of microphone are moving coil, dynamic, condenser, capacitor, and ribbon. Moving coil mics are inexpensive, rugged, and good for most sorts of signal. Condenser, the word condenser is an old-fashioned word for capacitor. Microphones used to be classed as expensive and delicate, but modern Chinese manufactured ones are in the same price bracket as a good dynamic. Large diaphragm mics sound smooth and full and are good for vocals. Medium diaphragm types are normally thought of as instrument mics. They don't have the impressive bottom end sound of the big diaphragm. Capacitor mics can either be true capacitor, meaning that the polarizing voltage in the capsule comes from a phantom power source, or back electret, where the capsule is permanently charged during manufacture. There is not a great difference in sound between the two types, but the true capacitor tends to be quieter in operation. Ribbon mics are expensive and delicate. Most have a figure 8 response and have a very low electrical output. Quality can be extremely good. So what is the purpose of a microphone? It's not such a simple question. If you are recording a string quartet, then the purpose of the microphone would have to be to reproduce the sound as it hears as accurately as possible. But if you're recording, say, a brass instrument or an electric guitar, then the purpose could be to reproduce the sound that you imagine you might hear when listening to the instrument. The simplest, and also one of the most difficult signals to record, is the human voice. The recording studio, of course, needs to be free from serious reflections on the walls. It also has to be fairly dead to avoid the sound being coloured by the reflections, and the singer needs to be fairly close to the microphone so that the direct path of the voice to the microphone is short. If a large diaphragm capacitor mic is used, and the vocalist is used to recording, then there is a good chance that the recording will be a success. But we have already made some enormous compromises compared to listening to a singer unamplified in the real world. In the real world, the performer is normally seen, and the visual clues picked up by the listener compensate hugely for the problems of intelligibility because of the reflections and distance. So already the recorded voice is by no means real. It is an idealized simulation. Taking it one step further, if we can compensate and make a voice sound more natural by eliminating reflections and having the microphone close, then why not go beyond this and enhance the sound of a recording? And that is exactly what we shall be doing for the rest of this talk. Mic amps. There is a lot of false technobabble talked about mic amps. The basic, conventional, professional mic amp is a preamplifier with a medium input impedance, extremely low noise, and a very wide variation of gain. All the really good ones achieve this by using 2 or more gain stages. This is because trying to get, say, 55 dB of gain from a single gain stage is too difficult to do and still retain good noise and distortion performance. The input impedance needs to be high enough not to slug down the signal from the microphone, yet low enough to realize good self-noise figures, and there are now integrated circuits that do the job well. The output from the microphone can be as low as -70 dB or as high as 0 dB, with anything in between. So the amp must be flexible. The conventional mic amp works as a voltage amplifier. That is, it senses the voltage generated by the sound in the microphone and amplifies it. The P10 and other TFPRO mic amps actually work in a slightly different way. They sense the current generated by the microphone, and in the first amplifier stage, they amplify the current before converting it to a voltage. Whether a mic amp sounds good or not is an interesting question. It's more than a simple choice. A lot less expensive mic amps don't sound good, for the simple reason that the design is overstretched. The designer has believed the spec sheets provided by the IC manufacturers and has tried to get too much gain from a single chip. This is very common in inexpensive preamps and mixers. The effect is that they sound slightly thin, and it's not until you hear a really good mic preamp that you realize quite how bad the bad ones are. And then there are the good ones. They can vary a great deal depending on whether they have a transformer at the input and what the amplifier input impedance is. All these things affect the sound. An input transformer tends to give the preamp a warm sound that is full of life. Variations in input impedance alter the character of the sound of passive microphones, dynamics and ribbons. The mic amps in the P10 have chunky transformers. Phase. The TFPRO P10 has both a phase inversion button and a variable phase control on each channel. These are really get you out of trouble controls that avoid problems where using more than one microphone introduces phase cancellations. These show up as thin, reedy sounding mixes. Compressors. Probably the single most important tool of the recording engineer is the volume compressor. But first, a couple of definitions, just in case you were a little hazy about it. A compressor is a variable gain amplifier that reduces dynamic range. That is, if you increase the volume going in by an amount, the output will increase by a lesser amount depending on the compression ratio. A compression ratio of 2:1 means that for an increase of 2 dB at the input, the output will only rise by 1 dB. A limiter is an amplifier whose output is restricted to a defined point. If the output tries to go beyond that point, then the gain of the amplifier is reduced to compensate. In the real world, a high ratio compressor works very much like a limiter. The attack of a compressor is the time taken for the gain to reduce after the input of a higher level. The release is the time taken for the amplifier to recover to its no signal gain state. There are 5 main types of compressor in use nowadays. The digital compressor, where the gain structure is carefully controlled and the attack and releases are highly predictable, and it doesn't sound too good. The FET compressor, unusual nowadays as they tend to be noisy and prone to high distortion, but they sound okay for some instruments. The tube compressor, expensive and unreliable, but make a beautiful sound. The VCA compressor, the commonest analog type, highly predictable and not very nice sounding. The optical compressor, my speciality, and in my opinion, by far the best sounding. Equalizers. The origin of the word equalizer comes from the film industry, where in the early days it was a challenge to get the sound of recorded speech to be the same when the film was edited. Different camera angles required different microphone positions, and so the sound had to be changed to make it all the same, or equalized. Like compressors, there are several basic types of equalizer. In outline, there are digital equalizers that are an attempt to mimic the best analog EQs, but in the analog domain, there are a number of configurations and types that are worth mentioning. The most notable is the Baxendale circuit that was developed in the 50s by Peter Baxendale, an engineer working for EMI in London. This was the first active or amplified EQ circuit that gave predictable and very good sounding high frequency and low frequency lift and cut. The conventional way to achieve variation in the mid-frequencies was to use tuned circuits composed of inductors, coils, and capacitors. Later, circuits improved on this by using active electronic models of inductors called gyrators. In practice, the very best EQ units, and I will include the TFPRO P9 in this, still use actual inductors even though they are expensive and heavy. The P10 EQ is intended for mild colouring of sound, and so it uses a combination of a Baxendale high-frequency end with 3 sections of gyrator-based mid and bass. Real world. It's time to put a voice in front of a microphone and think about what we're doing. Our brains imagine a sort of idealised sound of a voice. The extraneous noises are ignored and the voice is clean and pure. But this isn't true, of course. In the real world, there are all sorts of confusing noises and reflections, but to make our recording acceptable, we need to idealize it. so we place the microphone close to the voice. This has the effect of removing interfering noises, and it also softens the sound because of the proximity effect. If the sound source is very close to a microphone, there is a noticeable lifting of the bass response. Because of the proximity, there is also a problem with the wind blast from the breath. Many mics are supplied with foamed plastic wind filters. These are worse than useless. They are not very good at deflecting the wind. They affect the sound, making it dull. There are two types of effective pop shield. The first is a nylon stocking type, and the second is the expanded metal type. This is an interjection from Joe here. At this point in the lecture, Ted demonstrates a voice recording of his wife Barbara, and he demonstrates EQ and compression and a few other things. Unfortunately, I don't have that here, so if you're interested in that kind of stuff, you'll have to do your own research for it. But the concluding paragraph references this, and therefore I felt the need to interject and say this. Back to the lecture. Now, for the purposes of this demo, I actually recorded the voice with no compression. I don't normally do that. This is very much personal preference, but I like to apply just a little compression during recording. It helps to get the best level onto the digital track. Okay, so it's a hangover from the days of analog tape. I can try to justify that as well by saying that I like to use at least two types of compressor on a voice to make it interesting and punchy without obvious sounds of heaving gain stages. Most voices I record completely flat, that is, with no EQ at all. But if there are signs of low frequency problems, it's good to be able to use a high pass filter. The one with the P10 works at 75 Hz, which is a good standard useful frequency. I usually keep the EQ switched out when recording, unless the voice sound is particularly dull. If so, then it's okay to put in a touch of high mid-lift, say 3 dB at 6 kHz, just to fizz it up a bit. Ideally, I like to use a harmonic enhancer, just the merest touch during the recording, and this adds real life to the sound of the voice. When we come to the mixdown, of course, anything goes. Okay, there we have it, the final lecture from Ted Fletcher. I really do hope that you've enjoyed this series. I found it quite funny in the previous episode, lecture number 7, when Ted's son interjected about some of Ted's thoughts on things, and it's very typical of anybody who gets fairly high up in any kind of industry that they have strong opinions on things. You know, you need to have strong opinions on things, I think. That's not to say you shouldn't be willing to accept other opinions and have an open mind, but you know, you don't get far in a particular section of any industry without feeling confident in your knowledge of something. And I found that really interesting to hear Ted talking, even if some of it is conjecture. And I think he explains it in a way, and he prefaces his thoughts in a way that makes that acceptable. You know, he's not stating these things as fact, especially when he's talking about the ear. What he's saying is that often the way that we perceive sounds don't match up with the scientific number jargon surrounding the way, you know, the number jargon of a sound being received by an ear, if that kind of makes sense. And it's true, you know, when it comes to art, you know, visually and orally, there's emotion plays a huge part in the way that we look at sounds. And I think that marriage of science and sort of the technicality of and the electronics behind recording and emotion and sort of emotion is a really interesting marriage. And the way that Ted thinks about both of those things together is lovely. You know, I think that's a really interesting way of thinking about it, and it makes sense as to why the gear that he has been involved with is so important. And some of the projects, you know, if you listen to his episode where I interview him, he's been involved in numerous other things that are not to do with music, like in-car telephone systems and things like that. But he's not just as I've just said, he's not just a scientist. He's also thinking about things in an emotional way as well. He started out his career as a backing vocalist for Joe Meek, and that to me is a really beautiful marriage of taking the technicalities and the beauty of something and ending up making sort of great studio gear, essentially. So anyway, I'm waffling, but I find it really, really interesting. So next week, we're going to be getting back to normal interviews, and I've got a whole host of amazing guests coming up. And I just really hope that you've enjoyed this little series of lectures, and I like to think that these are now a nice collection of Ted's thoughts that will remain in the ether for a long time to come. So yes, that just remains for me to say a huge thank you to you for listening. If you'd like to get in contact with you, you can just speak to yourself. But if you want to get in contact with me, my email address is joe@allyouneedisdrums.com. I have a website full of free things that you can have, which is allyouneedisdrums.com. You can also read about the sessions that I do in my studio and all that kind of stuff on there. Huge thank you to Adam Mallet for the artwork he supplies to this podcast, to Joe Kane for the intro and outro music, and to Rory Hancock for editing and uploading the podcast and making it all happen. And again, thank you to you for listening, and I will be back next week. Goodbye!